Good morning, good afternoon, and good evening. I'm your host, Caitlin Stulick. I'm here with our presenter, Ted Huang, and our co-presenter, Angela Criswell. Thank you all for attending Rigaku's webinar series, Mastering CT, Advanced Techniques in Practice. In this webinar series, we will discuss advanced X-ray CT methods to overcome common challenges, including high-density samples, repetitive routine work, and dynamic CT measurements. In this episode, we will cover 4D structure studies with X-ray computed tomography. But before we start, a few housekeeping items. This is going to be an interactive session, and I will be posting relevant links in the chat window. We'll be taking your questions live during the webcast and answering them during the session, so please don't wait until the end to ask. Please submit those questions via the Q&A button at the bottom of your screen, as we won't be monitoring the raise hand function. We will try to answer as many questions as we can during the webinar, and we'll respond to any unanswered questions directly after the session is complete. If for whatever reason you have difficulty viewing the webinar live, please note that this is being recorded and you will be able to view the recording beginning tomorrow. Okay, and with that said, I will turn it over to Ted.
All right, thank you so much, Caitlin. And thank you everyone for joining for our episode today, 4D structure study with X-ray computed tomography. This is the third episode of our Advanced CT series. As you can see here, 4D structure, these are probably going to be the two keywords we're going to see a lot today. Now, before I even talk about 4D, I would like to talk about structure a little bit, because especially for non-destructively looking at the structure is a key factor for doing 4D studies. A lot of times you will need it, a lot of times they will just help you out a lot. So why is non-destructive structure study crucial? Let's look at the destructive ones first. Usually we'll start with your product or maybe your sample. And once you want to study its structure, chances are you need to do some sampling, some preparation. Usually it involves cutting it open, taking a small piece of it, and do some preparation like polishing before you can finally put it into the analysis tool like microstructure analysis tool, SCM, TM, and then have your result ready. And then that result hopefully will be helpful to your product. But usually at the second step here, the preparation of sample, you will encounter a lot of challenges. The first one, the obvious one will be, is it even representative of my product? Because it is a cut small sample, it's not your actual product. And sometimes you will wonder, did I actually do some additional damage to the structure during those process? To prove that's not the case, you have to spend more extra time, more care, more resource, just to make sure it's representative and it's not causing any error in the process. That basically translates to extra costs, not just a cost of money, but cost of time, cost of everything. And that's not even the cost of your analysis yet. That is just a cost to make sure this process is valid. Wouldn't it be nice if you can just skip it? Well, with some smart planning and with non-destructive structure study capability, you can skip this step and just look at your product, do the analysis, and get the results, hence getting rid of the extra cost. This means you have a non-interfering direct observation tool. Now, with this capability, then it opens up a lot of freedom for you to think about other opportunities of complex dynamic scenario setup. So it opens up the portal for you to do easier 4D studies. Now, in today's webinar, first, I'll talk about what exactly is 4D study. And once you know what 4D study is, we'll talk about why it is important both for academic and for manufacturing. And we'll see some of the 4D studies done in the X-ray CT. There are multiple kinds and there's a lot of different ones, but I'll go through some common ones and show you the examples and their challenges and their advantages. Finally, I'll showcase to you some experimental examples that I did and some of my colleagues at Rigaku did using the capability we have in the lab. Now first, what is 4D study? So this term has been kind of overused. 4D, you might have heard this term even when during you go to like a theater and they claim it's a 4D or even 5D experience, right? But in this case, the context of 4D study is fairly simple. It is 3D plus another dimension, in this case, time. So 3D and time, both together. Now, for structure study, let's look at time factor first. There are structure study that doesn't involve 3D necessarily, but they do think about time. First, the real time, meaning you have almost instantaneous or live structure information update of what is going on. So, for example, in some conventional microscopes like optical microscope and SEM, you look at something happens within the optical microscope or in SEM. That is one real-time study. Or you're doing radiograph or X-ray neutron diffraction, reading live. That is also real-time study. Now, it doesn't have to be real-time all the time. It can just be time resolved, meaning you have a periodic structure information update, not live, but still very frequent, or the frequency depends on the tool you're using. Like X-ray CT is one example. Now, if you just look at this list, you might ask, hey, Ted, then doesn't that mean CT is not as good because you can only do time resolve? What if I want to do live, do real time? Wouldn't that mean other tools are better? Well, here comes another factor of the 4D study, the 3D factor. Now, if you have to have 3D, the conventional tools like OID and SEM, individually, they can give you 3D if you do like fib sectioning all the time, but then you destroy your sample. You cannot look at it anymore. You have to prepare a new sample. So you lose the real time, the time resolve aspect. For radiograph, you kind of get more than 2D, but it's overlap, not exactly a true 3D fashion. X-ray and neutron diffraction, they do give you 3D information, but they're not exactly an imaging tool. So they are super powerful, but if you want an imaging tool, you have to go to CT. So these are the true 4D structure study tools, combining 3D and time. So what is 4D structure study? Very simply, it's 3D structure study with time-dependent development information. So it can be really straightforward. It can be really broad. Like today, you're looking at the sprouting of a seed or growing of a plant. If you scan it using CT during different stages of its growth, it is a 4D study. And would you look at that? Someone already did that. They scan a seed sprouting, germinating using CT to study its change. There are some other interesting examples, like I like drinking coffee a lot. How do we get coffee? Well, you have coffee beans, harvest it, and then bake it into different type of coffee beans. Like I like dark roast the most. Some people like light roast, but their structure change during this process. So you can also study how different baking at different temperature or different coffee beans change their structure. This is actually an example done by my good friend Nishan back at Professor Charles' lab. So now you know what 4D structure study is. With that, I would like to ask you some question. With that, let's hand it over to Angela.
All right. Thanks, Ted. So we're going to launch our first poll question today. And what we want to know is, have you done time-resolved experiments in your studies before? So yes, no, and if you're not quite sure, there's an option there for that too. So we'll just give everybody some time here to answer the question. So we've got a little over 50%, and it's creeping up 60%. So I'll give a few more seconds. 3, 2, 1, and in the poll, I'm going to share the results. So 67% of you have answered, and of that, about 40% of you say yes. In fact, you have done time-resolved experiments. 61% of you say nope, maybe not yet is the answer there. And everybody is fully engaged, so nobody said not sure. I'm going to stop sharing and send it back to you, Ted.
All right. Thank you, Angela. And thank you, everyone, for answering the poll. It really tells us a lot about where you're coming from. And I'm happy to see that a lot of people have already done time result, and a lot of you have not done it yet. But since you're here, apparently you're going to be very interested in this aspect. And hopefully the content I'm going to show you will be very exciting. So we now know about 4D study, 3D plus time resolved. But why is it important? Why would you even want to do that? Some people might think, oh, it sounds like something very academic. Would I even need it if I'm from manufacturing, if I'm for production? Well, you actually also can be greatly benefited from it. How so? So for a production perspective, if you have a capability to do 4D study, it can benefit you a lot if you do a lot of design, production, cycle integration. And if you're not doing a lot of iterations, you're just doing manufacturing in general, it still can provide you a lot of context on how your product operates, how they perform in real life conditions. And lastly, obviously, for research perspective, with the capability of 4D, there are some studies that was not possible is now possible. So we can do some really deep dive study using the 4D capability. So let's look at some example, or I should iterate more about what I meant, the integration of product design and production cycle. Let's say you have build, processing, and product process of your product. You first build it in a brand new way. Now you want to know how you build it. Is it good or is it bad? If you use a conventional destructive way to study it, well, you have your answers, but the thing is destroyed. So now when you try to study processing, you have to build it again, destroy it, get your result, go to the product, destroy it again, and get your result. And finally, get the full cycle. Now, it is very time consuming. And also, not to mention, you're making all these samples that make sure and prove they're all the same when you build them multiple times. Now, if you have 4D capability, you can just integrate it into one single straight line. You just do examinations throughout different process. With the time save and simplification, now you naturally will think about, oh, maybe I can include even the material development and the final redesign phase, and then put in some 4D studies just so that I have more information throughout this integration. For more concrete examples, let's look at maybe battery production. So starting from the raw material, making the coating and particles onto the cathode and anode, assemble it, packaging, and then actually use it, see its capability. Let's look at this part, the assembly. Let's say you make your powders and you spray coated it onto your cathode or anode material. You can use X-ray CT to look at the particle distribution and their quality. And then you're happy with it, you put it into assembly, and then in between the separator material, you're curious about, oh, how does the separator material looks like? And then next step, you finally package it and look at the packaging process to see if it damaged your product or caused anything that's undesirable. And if you're smart, all these three images can be from the same sample. It can be exactly streamlined into your production. You don't have to make additional samples out of this. And if you're interested in the operando or the actual operation study using 4D, here's an example. It's kind of in between research and manufacturing. This is a study of a battery material cracking and then how it correlates to its performance. You can see the voltage drop correlating to the spot, the researcher spotting the crack forming inside the material. Now, with those things clear, now you know how important it is. It's exciting stuff now. I'm going to show you what are some of the 4D studies that you can do using X-ray CT and what are people doing using X-ray CT. So 4D study, because it's just a 3D plus time result, it can literally be anything. But there are a couple ones that's very popular and people are thinking about doing all the time. First is mechanical testing. I'll show you some example that's ex situ mechanical testing. If you're not too sure what it is, don't worry. I'll also tell you about it. I'll show you some examples of ex situ mechanical testing studies. And then what are their advantages and challenges when you're trying to do ex situ mechanical testing. There are also in situ types. Show you examples, advantages, challenges, and the same thing I'll do for the temperature control. Show you ex situ, in situ examples, advantages, and challenges. Finally, some other type of 4D studies that's interesting, both ex situ and in situ, but they're not exactly under the categorization of mechanical or temperature. Now let's start first with ex situ 4D mechanical study. So because the ex situ, meaning it's outside of what is happening, is quite straightforward. It's before you do anything, you scan your sample first using your X-ray CT. So you obtain the pristine structure information and then take it out, do whatever you want ex situ, like shatter it, crack it. Then move it back into CT to see how it cracked, how it changed after you do your ex situ experiment. Now, in this case, the benefit really is in this stage, you literally can do anything. You can do all the conventional mechanical testing you want because your sample is outside. You just put it into whatever mechanical stage you have. The challenge comes in here, the transportation of it back into the CT chamber, because chances are the structure might not be as strong after your mechanical testing. So here's an example of ex situ testing. It's actually from my PhD thesis. This is a meteorite rod that I want to compress. On the left is a CT scan before it's being compressed. On the right side is the indication of how I did the compression in a conventional servo-hydraulic jig. So you can see in this case, I designed a sleeve that's just a bit shorter than the sample. So it has room for it to be compressed without interfering the compression, but still having a sleeve to contain whatever fragments that will generate after the compression. So after the compression, it looks like this if you scan it using CT, and just a side-by-side comparison showcase you looking at it from exactly the same angle, but now before and after you do the compression for the study ex situ. Now, this is just an external, but with CT, you have internal structural information too. So I was able to look at the internal structure, look at, oh, there are different phases in there. How do I change? Oh, yeah. So this phase 2, phase 1. How do they change and how do they interact with the crack differently? After I compress them, I can study them more in detail. But there's definitely something I still don't know, right? So what is the challenges and advantages of ex situ study? Well, the advantage is I'm free to use whatever conventional testing machine I have. In this case, I use servo-hydraulic. You can do bending, you can do impact study. The challenge is, well, how do you get the sample back into a CT in one piece, right? In this case, you have to design based on what kind of test you'd want to do. And also during the compression in between what happened, I really don't have any live view, maybe on the surface, but I don't know what's happening inside. But I was interested in what's happening inside. So I move on to doing it in situ. So in situ means on the spot, basically you're looking at it happening live. So in this case, we're not just scanning the sample itself, we're putting the whole mechanical testing stage inside our CT chamber. In this case, showcase you as an example, this is one of the Devon stage, Devon CT500. And this is where you put your sample in between the jig. You can do compression or tension. Now, the advantage is clear. Well, you don't have to move your sample as much, so it's more stable. But the limitation comes wholly in your setup. Now your setup, the stage you put in there, is a limitation of your test. How big can your sample be? How high can the load be? And what kind of geometry you have to design to fit into that jig? Now those are your challenge and your limitation. Now let's look at the example, continuation of my study. But before that, let's dial in a bit. Let's look at a bit more about the details of the challenges I talked about that's pertaining to the stage that you want to use. And it's actually the challenge I faced when I was doing this experiment. So I put the cylinder inside the jig and I want to scan it. So this is an indication of my cylinder of meteorite in between the compression stage. And then I scan it using X-ray CT. So I shine the X-ray source, both top and bottom, so stitch them together, get the X-ray through to detector. But here's some issues happening. Because the stage has to be strong, they're compression stage, they're tool steel or stainless steel, very strong material, but they are also very absorbent of X-ray. So in this case, a lot of signal actually got blocked in my CT scan. So if I just do it as is, my CT scan, my structure study will lose up to, in this case, 15% of the volume. I cannot see what's happening there. Well, in this case, this is my sample. Maybe your in situ test, you can design some other ways that you don't care those areas. But in my case, I cared. So I have to think about ways to kind of get around it. So the way I did it was I put some spacer block in between that's still strong, that can be compressed, not interfering with the study, but also lighter weight. And it's actually more lighter in density. So they are less absorbent of X-rays. So in this case, I get to see the whole sample now to have the full volume data to do the analysis. But you can imagine there's a lot of complexity going into this. So starting from the sample, when I'm designing my sample, I have to make sure it's completely flat. Otherwise, it's not going to have an even loading. So in this case, you can see if it's a flat sample in the CT, well, CT is actually also a good tool in this case to help me identify if it's flat enough. I will see this cross-sectional image. Everything is in the field of view, not out of focus. If it's tilted, not flat enough, you will see something like this. You have a blur at the edge because that side is just out of focus when you're trying to look at the cross-sectional view. And the complexity also comes from the spacer because now I just put additional things in there. The spacer also has to be flat. It has to be strong enough to not interfere with the study. So in the end, we actually did simulations even just to make sure it's not going to interfere with the compression of my meteorites, to go through a lot of challenges to make sure it works. So depending on your setup, you might also face this kind of challenges. But again, like I mentioned, it's tied to the jig and setup you use inside your CT chamber. So here's the result after we resolving all those challenges. I did in situ compression test, and this is one of the test results recorded shown on the right. And the left side is the force and displacement curve. And it's very slow, so I had to speed it up super fast, but you can see the seconds fly by and how I compress it immediately. At the end, it cracked. Happens way slower. You see it's actually 10 minutes, more than 10 minutes long, but I speed it up just so you can see the result. Now, to summarize in situ mechanical study, the advantage is also quite clear. We now have real-time, a live 2D radiograph we can look at to see what's happening inside the structure. And also, you don't have to transport your sample after it cracked. But the challenge comes from your scale that's limited to your setup, to your stage, to your city system, and also the design that's pertaining, again, still to your stage and what kind of study you want to do. Let's move on to the temperature study. Starting from ex situ again, now you probably know what's going to happen. You scan your sample, take it out, do ex situ temperature control, and then put it back into CT to scan it again. So the advantage is the same. You can do all the conventional testing with atmosphere control in the furnace for a very long time, you name it. But when you transfer it back into CT, or the time you need to spend to transfer might give you some challenges. You might think about, okay, is there still ongoing structural change during this process? If it's not, then great. This is a good way for you to study. So for example, this is data from one of my good friend, Professor Tsai. I actually did the scan for him. This is 3D printed ceramic materials. It's lamination. You can see the layers. So in between steps, green body is just as layered. We do multiple bakings. And in between baking, the structure doesn't really change. So we can do this ex situ study perfectly without worrying about the structure changing in between the stages that we move it in and out of the CT chamber. Now, this is a 3D view for you to see. You can see the layers getting less and less prominent because that's by design. At the end, it's centered. But you do have porosity condition change. That's why we were interested in analyzing it, doing some structure analysis on the pores, the size, distribution analysis. Now, ex situ advantage is still very similar to mechanical ones. You're free to use any conventional heat treatment, but the challenge will be, well, you don't have the capture of continuous structure change if there's any. You're limited to no live structure info because you have to scan it to see what's happening. So to do it in situ, similar to mechanical one, you put in the temperature stage. And here's an example that's again made by Devon and Devon temperature stage. This is where you put your sample. Advantage is you have live temperature control. You just do the temperature control inside your CT. So you don't have to worry about the lag in between your temperature treatment. The limitation is still at your stage, your sample size, temperature range, heat distribution, and how accurate the reading is that's telling you the temperature of your sample. So here's an in situ example. Actually, I did this with one of my good friends, Ame. We went to synchrotron to do this. So this is the picture of him cooling down in molten solder to look at the bismuth crystals crystallizing inside the solder. So this is a cross-section view of the CT. You can see the crystal growing as the temperature goes down. And this is 3D segmented data to showcase you the same pyramid structure, but in 3D, along with the temperature change. Now, so for the in situ temperature study, the advantage is you have live view, similar to mechanical ones. It's kind of the theme between in situ and ex situ. They kind of also compensate each other. You have live view when you're doing it in situ, but and also you don't have to worry about structure change in between your stages of moving sample in and out. But the challenge still lies in the scale of your setup. And in this case, reliable temperature control and monitoring is one of the key aspects when you're trying to do it in your chamber. Now, lastly, there are still 40 studies that doesn't fall into either mechanical or temperature control, like the coffee bean baking or the plant sprouting or growing we talked about earlier, right? So for ex situ study, in this case, you know the jig now. You scan it and take it out, do whatever you need. In this case, maybe it grow into a crystal or something, put it back into CT and scan it again and see how it works. So there are a lot of interesting examples. One of them is actually done, again, by my friend Raul back at Professor Charles' lab. He was studying honeycomb and how they were built. So he scanned this nascent particle hive structure and then put it back in incrementally so the bees can continue to build on this structure. Then we have a perfect 3D study of how these honeycombs are built. And also during building, they're not just adding more material, they also compact those hives. So in the walls, the porosity of the hive also changes. And here's a nice graph that he made to show the changes in different stages. There are stages that's more drastic, and there are stages that's more mature. And this is ex situ because, well, you cannot really put a beehive inside your CT chamber, right? So here's a video. I had to speed it up, but you can still see the growth layer by layer after it's built upon by the bee. Each time he put it back into the beehive, it grows more and more taller and taller. And you can also see the walls of the bottom part that's being compacted by the bees after each growth cycle. Yeah, so it's a really interesting example. Now, you can still do in situ if those factors you want to control can be designed to fit into the chamber. Now, this is an in situ example, again, coming from previous previous example I mentioned, the battery operando study. So in this case, they put the charging and discharging cycle capability into the CD chamber. You can see here actually rotating and scanning the battery material live and look at the structure while they're doing the cycling. In another case, this is done by another colleague of my, Professor Charles, previously during my PhD. This is a tensile stage, but with some atmosphere control to induce a corrosive wet environment to study stress corrosion cracking. So in this case, we were able to see how the crack advanced throughout time with the both combination of tension and corrosive environment. Well, that was a lot of examples, right? So don't worry if you missed something, you want to see it more clearly, we have recordings available after this webinar. But with this, I would like to ask you some questions using the polling question we have today. So with that, I'll hand it over to Angela.
All right, thanks, Ted. Those are really cool examples. So I'm going to launch our next poll question. And this one's, you can answer multiple choice. So the question is, which 4D studies are you most interested in? So I'll just read these out because if you're watching the recording, you can't see this poll. Are you interested in ex situ mechanical or maybe in situ mechanical? Are you interested in ex situ temperature control? Maybe you're interested in situ temperature control, or maybe you're interested in something completely different ex situ, or maybe even something other that's in situ. So, wow, we have half the people so far have answered the question. And as that creeps up, so I'll just give another 3, 2, 1 to give everybody a chance to answer. And I'm going to end the poll. So we have 60% of our attendees answering. In situ mechanical accounts for 69% answer. So that was the top winner. followed by in situ temperature control at 50%. So that tells us, Ted, in situ is more popular because ex situ mechanical accounted for 25%, ex situ temperature 11%, but there are some other experiments people are doing. And again, in situ others is 25%, ex situ others is 11%. In situ, the clear winner here is, I think, is Ted, what they're telling us. So I am sharing those results with you right now so you can see them. And I'm going to now stop sharing and send it back to you, Ted.
Okay. Thank you, Angela. And thank you, everyone, so much for answering the poll. It really tells us a lot. And it's really exciting to see that a lot of people are interested in situ mechanical testing. So kind of a small spoiler, I will show you how I did some of it in the later chapter of the webinar. But like I mentioned, this is actually a very broad study aspect, like 4D in general, time plus 3D. So you don't necessarily have to do in situ or ex situ. Either way, there's no one that's better than the other. A lot of times you can do both, right? So even if you're not just doing in situ mechanical study, I hope you'll be able to learn a lot through this webinar today. Now, not just for polling question to ask you a question, now you have a chance to ask me a question because we have been through quite a lot of things. I imagine you might have quite a few questions you have in your mind you want to ask me. So let's head for a small Q&A session here.
Okay, we have our first question. What is the maximum load cell that exists on the market?
Oh, I mean, that we have to do like marketing research on that. So I cannot give you a definitive answer. But my personal experience, I use one that goes up to 5,000 Newton. I know there exists something more. I think maybe 15K Newton. But you can also imagine kind of similar to a civil hydraulic setup. The larger it is, the larger the contraption will be. And to fit it into a CT system, you probably also need a way larger CT to do so. But maybe there are some people making even more than that, but those are numbers I can recall on top of my mind.
Yeah, I think I've heard of a 20K Newton, but I don't know that I've heard of one higher than that. But maybe someone could tell us if they've seen one.
Yeah.
Okay. We'll move on to the next question. Can you please share some inputs on 4D study for a product during its manufacturing for defect detection in the production line?
Oh, yeah. So defect protection. So in this case, defect is also quite broad, but I would imagine, for example, crack or porosity, those are perfect for integration into your manufacturing because they are very easy to spot using CT, and they're all very straightforward. There are also a lot of analysis capability nowadays on the market that's catering to that because they are doing automation. So sometimes those kind of crack or porosity can even be directly detected just using software without manual input. So yeah, there's definitely a lot of potential there, and people are actively trying to put it into defect analysis during the production.
Okay. Sounds good. We will get to the remaining questions towards the end of the webinar. Please remember to drop your questions in the Q&A box. And
yeah, there's another one at the end, so don't worry.
Yeah, we will move forward and then we'll get to those a little bit later, okay? All right, turn it back over to you, Ted.
All right, thank you. Okay, so last chapter, I'm going to show you some 4D X-ray CT experiment examples that I did here in our office here with the Rigaku Rigaku hardware and capability. And also some of the 4D studies that's done by my colleague Aya previously. There are some ex situ examples. I feel like that's a good complementary to show you both in situ, ex situ capability and what you can do in both cases. So this might not be that as interesting as a honeycomb study, but I will tell you step by step the setup and what I'm considering at each step and what you might also think about when you're trying to do so yourself. So here, mechanical compression test, we do it inside our CityLab HX here. You can see this is a picture of the door open with the sample stage. Where you put your sample is right here. We have a rotational stage to rotate everything. with the combing X-ray source, China combing the catheter on the other side to pick up the signal. Now, this is not a compression stage or in situ stage you see here. This is the one I was using. This was the Devon CT500. So with a closer look, this is the bottom stage. So the load cell and the motor is at the bottom stage, and you will put a top kind of cap and then screw it in. So it's the top stage, and you push against it on the towards the top. This is the area for this stage where you put your sample. This one, CT500, this only has like a 500 Newton max load because it's just quite a small stage. And you have a 10 millimeter diameter area where you can put your sample. So with this kind of information, you can try to think about, oh, what kind of sample you want to design. And also the travel distance. In this case, for this jig, the compression mode, I only have 10 millimeter travel distance. Meaning when the whole jaw is open wide, it's only open to 11 millimeter. And then it closed all the way down to only 1 millimeter. Meaning if your sample is 12 millimeter, it wouldn't fit even if you open it all the way. If your sample is less than 1 millimeter, it wouldn't get compressed even if it go all the way down. So these are some numbers for this particular jig. And with this is what I look at first, right? Because I'm thinking about, okay, if I want to compress or do any tests, this is my limitation of the stage. Like I mentioned before, doing in situ testing, a lot of the limitation challenges and the ways you can show your creativity is pertaining to the stage you're using. Now, for here, this is the sample I put on. So in this case, I just want to showcase something being pressed. So I just want to let's compress the spring so you can see clearly it's being compressed, right? But then you see something, okay, well, what is that blue thing that's on the side? That's not a spring. So those are some putties I put there to prevent movement. Now, this is by no means an elegant way for you to do this. You have to put more thought into it. But let me tell you why I did that at the moment when I was doing this demonstration. So for an ideal world, for an ideal sample, you have very flat top and bottom spring. When you compress it, this is what you expect to happen, right? But chances are, most likely in real life, that's not the case. Your spring is going to be a little bit tilted, a little bit not even. So when it's being compressed, when the whole stage is moving upward, there will be contact on one side first. And in that case, those sides are experiencing some load. And what would happen if you do that? Even if imagine you're pressing on the spring on the table just on one side. Well, you'll squeeze it out. You'll squeeze it outside. Now, in this case, for this Devon stage, it has a sleeve outside, so it's not like the spring will just shoot out and destroy things. But this will still cause the whole experiment or the demonstration or compression to be invalid, right? So you have to find some way to stabilize your sample, and ideally, it's not going to interfere with your mechanical testing. In this case, I just want to fix it there. So I'm putting some putty there to increase the friction, and so that's not going to move around. That's it. That's why I put it there. So this is how you want it to compress. This is not how you want it to happen. Okay, with those set up, I put the top hub onto the stage. What else should I do? Do I just start my experiment and start turning my CT stage? Well, definitely not, right? Because now you have a whole compression jig in there. Look at the size of the spring and the size of the whole compression jig comparatively. You have a larger volume on your rotational stage. And also you have a wire because you have to control the compression stage. So before I do anything, you have to carefully examine the clearance. Not just if it's not interfering with things, but also see if the cable is tangling with other things or other stage. So in this case, it's actually going to reach the end of rotation. Looks almost like it's tangling into something, but it stops there. So I know it's going to be okay. So you have to check the wire tangle collision risk. And once those are confirmed to be not the case, well, now you can get into the actual in situ experiment to the control interface. But before that, you probably want to do a scan before you do any compression test. In this case, the spring will just bounce back. I can do it multiple times. But for your more destructive testing that will crack your sample, for example, you definitely want to scan your sample first, retain its pristine structures. In this case, I scan the spring. Quite straightforward. It's just a spring on the right side, segmented data, just showcasing you how it looks like. Now, we can start our test. So let me change to pointer so I can look at some. So here on the left, this is the compression interface of the Devon. It's quite analogous to many of the control interface of a conventional hydraulic jig. You have force control, you have compression mode. This one does also have tension mode. You can control extension, do cyclic load, and so on and so forth. And you can change the axis to be either time, extension, or force. In this case, I just want to do simple compression and see what's the force. So I just give a command saying, hey, move to this distance, this extension, so it will compress. And even with that, I still have to speed it up. Otherwise, it's going to take too long. I'm already using the fastest, the most aggressive displacement rate, and also the least intense sampling rate. But you can fine tune it so you can get all the detailed information of your compression or tension testing. And it can be outputted into an Excel sheet, a CSV file. So you can plot nicely instead of just using the visualization here. So let's play the video side by side so you can see what happens. When it starts compressing, you can see the load start going up. On the right side, you can also see gradually the spring getting compressed. And just a side note, in this case, this is a demonstration. This is only going to go up to about 2 Newton. So when you know you're only going to need such a low load, in this case, maybe even 500 Newton is a bit too much. Maybe you need more sensitivity. Maybe you need actually a smaller stage. On the contrary, if you're going to compress something that's very stiff, then you definitely need a larger stage. Now, you can see after compression, this is the linear curve because, well, it's still a spring. Just to show you at the end, the slope actually kind of changed a little bit throughout the linear portion. That is because you can see here, you can kind of see also in the picture, at the end, the whole spring is squeezed and compressed into the pulley I put there to prevent movement. So the pulley definitely messed with my load reading. So just to tell you, this is the way I just want to demonstrate the things that you need to think about, but this is by no means a perfect solution in this kind of situation. Now, after compression, obviously you want to do a scan after this, so preserve the structure of the as compressed or as tested structure. Then you have the structure to do your 4D study. In this case, I just throw both structure into a simulation, find an element to do a very simple low simulation to look at the von Mises distribution. And you can imagine all the applications that you can do in all incremental stage instead of like me just doing all the way compressed. You can stop it at intermediate stage and then scan the structure and see how the structure changes. Now, this is in situ and with a jig and setup and everything. But if you don't have it and you just have X-ray CT or you just want to ex situ, you definitely can. So here's an example done by my colleague Aya previously. This is an ex situ study that's very interesting. This is looking at bread dough fermentation. In this case, the CT is also different. This is CT Lab GX. This is a gantry system, meaning the sample stages are moving. It's moving the source and detector. So here, this is where she put the bread dough after you knead the dough and with some yeast in there. So it's starting to ferment. And then we scan it. She scanned it with different time intervals to look at the porosity development. So this is the dough, a close-up view. So with 0 minute, this is what it looks like as you roll it with the yeast. And then gradually with 20 minutes, 50 minutes, 80 minutes, you see how the porosity changes, how the bread puff up, the dough puff up. It's not the bread at this point because I haven't baked it. But after 18 hours, you can see those are more more similar to the kind of bread structure you're expecting in a delicious bread, right? And with that, you can also do analysis. In this case, she did the segmentation of the dough and voids to plot the development of the void volume throughout time. And another example she did was actually temperature ex situ 4D study. In this case, it's not the dough, but a salami. So a pre-cooked salami, she scanned it, and then she take it out to do some cooking. So this is a 30-degree structure she scanned. And as she cook it gradually and increase the temperature and scan it again and again, you can see as the temperature heats up, the structure also changes, the fat in there melts. And this is what it looks like when it's cooked and it's cut open. And she also plotted some data of the void inside, but in this time, not pertaining to time, but correlated to temperature that it has experienced. Now, with all those examples and all the talk today, I hope you have learned what it is 4D study and why it is important for both academic and also production standpoint. Some of the examples of 4D studies in X-ray CT, both ex situ, in situ, mechanical temperature, and some other more interesting ones, the other that's not mechanical temperature, like the beehive, so to speak. And some of the examples that I show you using the capabilities we have in the Woodlands office here at Rigaku. And with that, I would like to go through the final polling question before we head into the Q&A.
Yeah. Okay. And one thing before I launch that, I just want to say these Debon stages were loaned to Rigaku from Debon. They're very kindly, and we are thankful to have them to do these experiments here in our laboratory. So with that, I'm going to launch the last poll question. And this is the end of the series. So we'd like to know what webinar topics you would be interested in seeing us cover. So I'm going to leave this poll question open, and you can make suggestions while we answer some questions. So please, if you have some ideas or thoughts, please share them with us, and I'll send it back to Caitlin and Ted, and you can answer at your convenience.
Yeah, so we're always eager to know what you want to see next related to X-ray CT. So hopefully next year, or maybe even sooner, you'll be able to see us making webinar series that's exactly the kind of topic you want to see.
Okay. How about the next slide now?
Okay. All right. So with that, let's head into the final Q&A for today.
All right. We will get back into questions. We have one asking, how do you design 4D samples to properly follow conventional testing methods?
Yeah, that is actually a really good question. It's also the kind of challenge I faced during my PhD when I'm designing samples, and I was designing for both ex situ and in situ, right? So for ex situ, you have an easier time because ex situ, you take your sample out and you're using still conventional testing mechanisms. So you can try to just fit, and because you have to use conventional testing mechanisms, you just follow the protocols or established standard. But when you're thinking about in situ, then there's a lot more challenge since it's limited to your stage. Like my meteorite rods, for example, the rod cores are saying, oh, you make certain 3-inch tall rods to compress. I can't put a 3-inch rod inside my in situ jig. So what I did is I still follow as close as possible. And the ones and the reasons I didn't follow through, I have to put in the effort to make sure, okay, that makes sense and why I'm not following it. In this case, I make the sample downscaled. I still follow the aspect ratio of the compression cylinder, but because it's a precious meteorite, I don't have the material to make large samples, so it also makes sense to make it smaller. But in general, two sides. Ex situ, follow the standard as is traditional standard as good as possible since you're using ex situ anyway. For in situ, imitate the standard, but still design it for your in situ stage.
Okay. And our next question is, can all of our CT systems do in situ analysis or only our higher end models?
I would say the answer is all of them can do, because you're saying just in situ, you're not saying the stage has to be, you can just borrow a stage to do it. You can always make custom stages like some of the studies I just showed, because 4D in situ study really is just you do something inside a CT chamber. And you can do that in any CT chamber as long as you have the stage and you make it. And like the study, one of the study we just showed, like the battery study, I think they actually made their stage themselves. You can, if you remember, there's some wire attached to it, and that's it. You just have to let it fit inside the chamber, because that's one of the advantage of CT. It's scanning whatever is on the stage that's rotating, and whatever you're doing on the stage, it's up to you. So yes, straightforward answer is yes, you can do it in all models of our CT. But I can also tell you that at the moment, if you're thinking about this immediately available stage, like a Devon stage I showcased you, I think we only have 2 models that can fit it right away. But the other models people do in a customized stage into it.
Yeah, like the HX, it's a smaller chamber, so it fits a couple. One of our larger ones can fit all of them. But so the Otoyama study that you shared there, Ted, with the battery, that was made in-house. So you almost become your own, put your engineering hat on, your MacGyver hats on, and you can probably design whatever you need.
Okay. And we will move on to the next question. Are there any risks for in situ CT scans, for example, electrical shockwave during CT measurements?
No, because CT, so it's like this. Your stage it's a rotational stage, plain and simple. For your X-ray CT to function, the X-ray turns on the source side, the detector side, you pick up the signal. Itself, source and detector itself is not interfering with your stage. So it's basically similar to any electrical thing, like it in a it just contains electricity. So if you do something like temperature stage, you have cooling water, then you have to not make a leak. So you might electrocute, electrocute if that's the case. But there's no special precaution specifically for CT in this case. It's just general safety for doing things within within the device that's having electricity in it. That's it.
Okay. It looks like we still have some time, so we'll just keep going. Next question is, how do you represent it as 4D in the software?
Oh, how do you represent it in 4D in the software? So again, it depends on what kind of 4D you're doing. So let's just say today you have a very vivid, directly visible structure change. Like what I did in the meteorite rod compression, right? I see cracks, but it's still the same meteorite rod, I can tell. So you can digitally align your data as good as possible and then see the changes. And kind of like the honeycomb one that my colleague Raul did, he basically aligned the structure and then layer it on top of each other so you can see how it progressed. But how do you align them depends on your sample and how easy it is. If you're doing production model, you're manufacturing, then then you're lucky because chances are you even have CAD drawings you can align to. But if it's more free form study, then it's harder to directly have a good overlap. But you do have the digital data available all the time because you basically preserve them in digital space and you're free to manipulate them whichever way you want. So that's a good way to overlap them digitally and show the difference in that digital space.
Okay. Moving on to the next question. Does the rate of loading depend on the scan speed of the detector used in the CT scanner?
So they are separate. You definitely need to consider it depending on what you want to do because this is like the speed of taking photos. And with this, actually, I would recommend you go to the link that Caitlin shared earlier of the webinar that Aya did. Some of the example of the bread dough, for example, comes from that, where she talked about some of the consideration of your acquisition speed and the rate of your structure change. Because kind of like taking photos, if the thing that's happening is too fast, obviously you cannot really capture it with a slower scan. But in the case of compression, there's no direct tide just built in the system. It is more like you have to think about it if it's going to work for your study that you're looking for. And yeah, if it's happening too fast, then even using SCM or even using live video might not give you a lot of insights. But there's no direct connection. It is something you need to consider yourself.
Hey, Ted, as a follow-up question, when you were planning your mechanical studies, how did you determine what your step size should be for each when you increase the force? Because
Mhm.
I mean, you could end up with 1,000 steps if it's too small, or too much and bypass your crack. So
Yeah.
what are your thoughts there?
Yeah. So in this case, for commercial aspect for manufacturing, obviously you want to save your time. So you use the fastest acquisition you can get away with, and that still gives you the structure you want. For my study, because it's a PhD study, it's purely academic, I just use the finest, the slowest that's available. So I have all the data.
Oh, wow. How many
That's what I
scans did you collect out of curiosity then?
In total, there's also multiple samples. I think there's probably
so you can end up with a lot of data.
Skin wise is probably close to 20 something, 30.
Interesting.
Yeah. But not all of them are useful because there's some of them we're like doing intervals in skin. And in the end, we look at the structure like, okay, during this stage, there's actually no visible structure change. And then there are stages, we actually notice now this is where the crack starts happening.
Gotcha. Yeah. So sounds very time involved and a lot of disk space and data analysis. So
yeah, I mean, but that is because that's kind of like the highest standard for because research, right? You don't want to miss anything. You have the time to devote in that, but this is not necessary for all the 40 study people are doing.
Absolutely, yeah. Well, thanks for satisfying my curiosity on that.
You're welcome.
Okay, looks like we have time for one more. What is the most critical challenge to address when performing 4D studies?
Okay. Yeah. So you can probably already tell there's a lot of things to consider all the time, depending on what you're doing, because 4D is still a big umbrella. But just to make it simple to summarize, if you're doing ex situ, the most critical thing you have to think about is how do you get it back into your CT, the transportation. If you're doing it in situ, the most critical thing is how do you make sure what you want to do works inside your contraption. So transportation for ex situ, sample setup and experiment design for in situ. These are the more critical aspect you need to pay attention to. Obviously, there are other things that are also important, but I think if you want to summarize, those are the two.
All right, thanks. Hey, by the way, anybody want a last minute answer? I'm about to close this poll. And thank you. We've got 19 suggestions here, Ted. I'm excited. So I'm ending the poll now.
Thank you, everyone.
Can't wait to have a look at them. Thanks, everyone.
Okay. Well, thank you, everyone, for joining us today. We will follow up with any of the unanswered questions following this webinar, and the recording will be available tomorrow. Don't forget to subscribe to our newsletter. I'm going to drop that link in the chat window now, and we look forward to seeing you at the next one.
Bye, everyone.
Bye,
everybody.
Thank you, everyone.